Okay, another oscillating system we talked about was a pendulum. Okay, so this is called a simple pendulum. Okay, now the reason that this is called a simple pendulum is because it's just a long string, okay, with a little point mass at the end. Okay, it can't be something like the size of your shoe. It has to be a long string and a point mass. Okay, now how long a string? Well, in other words, the size of that point mass, okay, that can't be comparable to the length of the string. Okay, so you have a long piece of string and a little dot. Okay, so we want to find the period for the simple pendulum. So what I did is I drew a picture of this pendulum rotating or oscillating back and forth. All right, so this is what I did, is I drew the forces that act on that little bob. Okay, so besides the weight, okay, we have the tension here. Okay, I don't really want to call that a capital T because I'm using a capital T for the period. Okay, so I identified the two forces acting on the pendulum bob. So I have the weight of the bob and I have the tension in the string. All right, and what I'm going to do is I'm going to write down the torque about this axis up here. That's my support point. Okay, the torque about axis A. Remember, torque is always force times the moment arm. Well, you have two forces. You have the tension and you have the weight. Well, the tension passes right through the axis of rotation, so it causes no torque about that point. The only force that causes a torque is the weight. Okay, so there's my force, and I have to find the moment arm. Okay, so here's my line of action. Okay, for the weight, there's my line of action. So you need to draw a perpendicular line from the axis of rotation, right there, to my line of action. Okay, so that's my moment arm right there. Okay, so what I did is I drew this angle theta from the vertical, okay, along the tension of the string. All right, so my torque is my force times my moment arm. The moment arm is shown, all right? But that's not exactly complete. I actually have to include a minus sign, okay? All right, so the minus sign does the same job that the minus sign did in Hooke's law, okay? So remember, with Hooke's law, okay, you had a spring, okay, and if the spring was pulled off to the right, spring force is back toward equilibrium. If the spring was compressed to the left, the spring force still pointed back toward equilibrium. Okay, same thing we have here. So in this picture over here, okay, the torque due to mg, okay, about axis A, would be a counterclockwise torque, meaning that if you held this, okay, and let it go, all right, it would tend, the torque due to mg would tend to rotate the ball back toward that center equilibrium point. Okay, again, that's where the bob likes to just sit there if you're not going to let it go. Okay, if I bring it over here, okay, and let it go, all right, I have to draw the same mg. Okay, not worried about that, but the torque due to this mg would be clockwise. It'd be in a direction to bring it back toward that equilibrium point. Okay, so the minus sign is there to indicate that that torque, just like this whole business here, okay, that torque is a restoring force. Okay, if we ignored that minus sign, or if we left it out, that would say that this mg, okay, that mg right there, causes a counterclockwise torque, and it would keep exerting a counterclockwise torque and spin it around and around and around in a circle. Okay, and that doesn't happen. As soon as this thing passes that center point, the torque is now clockwise to bring it back. Okay, so the minus sign, just like that one, okay, is there to indicate that the torque is a restoring torque. Okay, so that's my torque, minus mg times that moment arm. Okay, so what we have to do is I took this picture up here, took that picture, okay, and I redrew it down here but without the forces. This is what I have, is I have, there's my vertical line, okay, here's my vertical line right there. That's the line along the string, that's the line along the string, that's the length of my string, okay, right there, all right. And then, instead, okay, if I look at what this bob does, what path does that follow? Okay, Well, that's an arc, right? It's part of a circle, right? So that would be my arc right there, all right? So what we're going to do is we're going to use a small angle approximation. So instead of bringing this thing all the way out here and letting it go, okay, you're only going to bring it out a little bit, maybe over to there, okay, where your hand would be, and let it go, okay? So this is what the small angle allows us to do. And you can see this in our textbook as well, okay? So here, looks like I have a sector of a circle, okay, like a piece of pizza, okay? But if the angle is small, okay, if the angle is small, then if I draw this line, okay, if I draw that line, all right, obviously in this picture above, that length is not the same as that length, okay? That length and that length are different. Okay, that's a straight line, that's along a curve. But when the angle's small, okay, that straight line, okay, is almost the same length as that arc, okay? So in our picture above, okay, in our picture above, that moment arm is the same as that length. Okay, so down here, that moment arm is that length right there. When the angle's small, that arc is about the same as that length, that little leg of the triangle, okay? Okay, so we know that for a sector of a circle, okay, we did that in the rotation chapter, that this arc S, okay, in geometry class or trig class, the arc length is equal to the radius times the angle theta. Okay, so S is equal to r theta. Well, what plays the role of r? Okay, L, the length of the string. So instead of r, I'm going to put in L. So this little arc length, okay, that arc length is the radius, which is the length of the string, times theta. But when the angle's small, that arc length is approximately the same as the moment arm. Okay, so our moment arm, therefore the moment arm, is L theta. So where I had my torque, right there, okay, that moment arm right there is L theta, okay? So now that gives me the torque due to the bob, a little hanging bob, about our axis of rotation, okay? Okay, so this is what we have. Why did we do all that? Okay, so this is the torque, okay, that's our pivot point. This is the torque due to mg for our pendulum. Okay, it has that form. So we're trying to make the connection between what we did with the mass and the spring, okay, and the period we got for that. I'll put that over here. Okay, and the period we got for that compared to what we're trying to find the period for the simple pendulum. Okay, when we had the Hooke's law for the spring, the period ended up looking like this, 2 pi square root of m over k. Okay, so when we went to the linear world, to the rotational counterpart, we saw how some things mapped up. Okay, well, force, okay, now we have this torque expression, okay, so force now looks like it got replaced with torque, okay, instead of position for the spring x, now we have angular position, okay, for our pendulum, okay, so position looks like it turned into angular position, okay, and then instead of having the spring constant k, we have this stuff sitting here. Okay, so let's see how we can use that. So here's the period that we came up with before for the mass in a spring. All right, so this k here was that. Well, maybe the stuff that's on the bottom is that stuff right there. Okay, okay, so that's the connection we're making. Okay, so we have a k here, that's the constant in front. So when we write the period for the simple pendulum, right, there's our simple pendulum. The denominator is that stuff right there, okay? Now, what goes on the top? All right, well, here, it was the mass of the oscillating system, okay? Okay, well, we went from force to its rotational equivalent torque, so in the previous chapter, the rotational equivalent of the concept of mass was that idea of moment of inertia, okay? So perhaps it's the moment inertia that's in the numerator there, okay? Now, how do you find the moment inertia? Okay, from our earlier chapter, you go to each point mass and then take the distance from the axis of rotation of that point mass and square it. So I'm going to calculate the moment inertia about axis A for that point mass. Okay, I just go to the point mass and multiply it by the distance from the axis out to that point mass, which is L, and then I square it. So the moment inertia about axis A is ml squared. So that's what I get to put right there in the numerator. Okay, I put ml squared. And the bottom I have mgl. Okay, so the masses drop out, and I wind up with the period for a simple pendulum. Okay, so if I take a string, okay, and hang a little mass from it and let it go, okay, the period, t, only depends on the length of the string and what planet you're on. Okay, it doesn't depend on the mass, and that's not obvious at all. Okay, and one of the reasons is when I let this thing go, it has potential energy here, then it has kinetic when it gets to the bottom, okay, and then it has potential energy when it stops, and it goes back and forth and back and forth, and that would be independent of any object that you put there, okay, independent of its mass as long as there's no friction at the pivot point, okay. So we can actually use this expression to calculate little g. All right, so back in chapter 2, right, remember our g was 9.8 meters per second squared root 1 to g. How could you measure that? Okay, the quickest and easiest way to measure little g is with a long string like your shoelace and something maybe heavy and small that you can tie in the bottom, okay, and pivot or oscillate back and forth. So what I did is I took this expression and I squared both sides. So you got t squared, 4 pi squared L over g, and then I solved this for g. Right, so cross multiply by g, okay, that gets rid of that, and then divide by the t squared, okay, and then divide by that. It's just, right, you can just do the algebra, that's no big deal. So that gives you g, okay, for where you are. So you can take length of the string, okay, take a shoelace, tie something small onto it that's not that large, okay, remember you want it small compared to the length of the string, okay, and then you sit there and measure the period. Now, best way to measure the period, okay, instead of going click, 1, 1, okay, that wouldn't be very precise. So what we do is we're going to do the same as we did in the lab, is you measure 10 cycles, okay, so this thing just goes back and forth, okay, and you get a timer, okay, and you go click, right when it's there, you go click, and then 1, 2, 3, 4. You do 10 of those, okay, you'll get the total time, okay, is some number. Then the period is your total time, okay, total time divided by 10, all right? So I'm going to show you a video where you know the length of the string, and you can measure the period, and you can actually calculate g using just a stopwatch, okay, and a ruler to measure the length of the string. Okay, so we're going to use that expression, okay, to calculate little g. All right, so I'm going to show you a video. There's a little pendulum, okay, or a little pendulum bob, okay. L is the length of the string, so it's about 44 centimeters, and it's released here from rest, and this thing's going to swing back and forth, okay. Now again, it wouldn't be very precise to just measure one cycle, okay. You're going to measure 10. Right? So you're going to measure 1, 2, 3, 4, and so on, okay? So, and it doesn't matter when you start. This thing can be going back and forth, okay? And you can decide to start right there. Click. 1, 2, 3, 4, and so on, okay? So you're going to measure 10 periods or 10 cycles, all right? So I'm going to play the video, okay? You can rewind it a couple times trying to figure out what's a good place to start. So what I do is the person releases it, okay? And I wait maybe 1 or 2 swings, okay? Maybe they release it, and then I'm going to start click, 1. Whoops, I messed it up. See that? They release and it goes click, 1, 2, 3. So it doesn't matter when you start, as long as wherever you start, that's where you count. Or you want to start when it's at the bottom. They release it here. You can go, they release, click, 1, 2, 3, 4. So sometimes it's easier to pick an endpoint. They release it here, let it go, click. 1, 2, 3. Okay, so watch the video, and I want you to count 10 cycles. Okay, so when I count at 10 cycles, I got about 13.3 seconds. Okay, so the period, capital T, is that total time divided by 10. So that gives you the period. All right, so I'm using this expression. Okay, I know the length of the string is about 44 centimeters. Okay, I use my stopwatch to get the period. Right, and I get 9.82. Okay, so the two sig figs, I get 9.8. So if I compare the 9.82 to the 9.8 or 9.80 in the book, I get less than 0.2, or I get about 0.2%. Okay, and then you get to put a smiley face on that. Okay, so just using a piece of string, maybe your shoelace, and something small, okay, not too light, you don't want a paper clip because there's too much air resistance, but something small and heavy enough, you can calculate that little g probably wherever you're sitting right now to within like 1%. Okay, I want to look at the energy of our simple harmonic oscillator, okay? Because it would make sense that if this thing is oscillating back and forth, okay, if you stood in front of it, it would knock you over. That thing has some type of energy, okay, associated with it. Okay, so you know that if you have a spring, and again, if you don't have a spring handy, you can try it with a rubber band, okay, or something elastic, all right? You can use your sock, okay? It doesn't act exactly like the Hooke's law minus kx, but you can feel the resistance of it, right? You can't compress your sock, and you can't compress a rubber band, but just try pulling it, okay? So if you take the spring, that's its relaxed position, you pull it to the right, okay? You're doing work. You're doing positive work to stretch the spring, okay? If you compress the spring, okay, if you push it that way, okay, then you're doing positive work to compress the spring. Okay. Remember why you're doing positive work, because you're exerting a force in that direction, you're moving that direction. Same thing here. You're exerting a force to the left and you're moving to the left. Okay. Now, the work done by you on the spring, okay, is stored as a potential energy in the spring. So you remember our projectile launcher, okay, that we looked at, okay. When you load that thing with your hand, okay, you push your hand, okay, and you're loading that spring, okay, you have to push hard on the ball that's back up against the spring, okay? So you're doing work, and then this thing clicks and stays in one position, and then you walk away and the spring stays there. So the work done by you to compress the spring is now stored as a potential energy in the spring, okay? How do you get the energy back? You lift this little lever, and then you get it back as kinetic energy, okay? So remember, in magnitude, okay, the spring force in magnitude is kx, but the work done by the spring, okay, is the spring force, okay, times the distance through which the spring is being stretched, all right? But when we wrote that in the energy chapter, okay, the component of the force along the direction you're moving, okay, times that distance, that only holds for constant forces, okay? The spring force is not a constant force. It depends on how far it's being stretched, okay? And again, you can actually feel that with a rubber band, okay? If you stretch the rubber band, okay, it costs you a certain amount of force to stretch it. Now, if you try to triple how far you're stretching it, okay, that you can feel the force getting bigger and bigger, okay? It's definitely not a constant force. Okay, so remember in the energy chapter, let's say you applied a 10 Newton force and you wanted to move this thing 3 meters, okay? The work done was the component of the force along the direction you're going, that's your 10 newtons, times that 3 meters, okay? So it was 30 joules. Now, if you plot it, the applied force, okay, as a function of how far it's being pushed, okay, there's your 10 newtons, okay? That's a constant force. So that graph is just a straight line, right? But you found that the work done by you, okay, this is the work done by you, your finger force is 30 joules. Well, that's the same as doing 10 times 3, okay? 10 times 3 gives you 30, okay? But 10 times 3, that's just the area of that box, okay? So the work done is the area under that line. Okay. Now for our spring, the magnitude of the spring force is kx. Okay, so if I plot the force versus the distance that's being stretched, okay, it's not horizontal like that. It's a function. Like remember from algebra class, y equals 3x, right? Looks like that. So that's not a 3, okay, it's a k, it's a spring constant. So it still is just a line in the xy plane, okay? So now we know how to calculate the area under that line, okay, because the shape of it is a triangle, okay? So the work done by the spring, represented by the area under the line, is just the area of the triangle, 1/2 the base times the height. So 1/2, the base is x, okay, and the height of that function, okay, right there, okay, that height is the value of the function, which is kx. So in magnitude, the work done on a spring or by a spring, if you're moving it from its equilibrium position, okay, in magnitude, is 1/2 kx squared, all right? So when we were moving the spring, or let's say compressing the spring, okay, in our projectile launcher, there's the spring, there's our hand, we're pushing the ball in that direction, okay? The work done by us on the spring was 1/2 kx squared, okay? Work done by us is now stored as potential energy in the spring. So we would say potential energy in the spring is 1/2 kx squared, all right? So remember we said that only conservative forces have potential energy functions, okay? So gravity is a conservative force, okay? Its potential energy function is mgh, okay? The spring force is a conservative force. Its potential energy function is 1/2 kx squared. So in our projectile launcher lab, okay, here was our projectile after we compressed the spring, okay, all right. Now you're going to release the little lever here, and this thing's going to come flying out, okay, and we want to find the launch speed, all right. Well, we know that the only way the energy can change is if there's non-conservative forces that do work, okay. Well, the spring force is pushing on it, but the spring force is a conservative force. So there are no non-conservative forces that do work. So initial energy equals final energy, okay? And the ball's not going up or down, so I don't need to worry about gravitational potential energy, okay? So the initial energy here is all potential energy stored in the spring. When it leaves right there, okay, the final energy is all kinetic, okay? So if I put in my initial potential energy, 1/2 kx squared, equal to my final kinetic energy, 1/2 mv squared, okay, get rid of the halves, then I can solve that for the speed v, right? So we did that lab if the manufacturer gave you the spring constant k, and you can measure with a ruler how far back you compress the spring, okay, then you can measure the speed that the ball comes out. Okay. Now, when we did that lab, I had asked, why doesn't the manufacturer print the launch speed on the side? Okay. And one of the main reasons, okay, besides that the spring can change over time, okay, the main reason is that M. Okay. They don't know what you're going to stick in there. Okay. Either it's the little yellow plastic ball, or you could stick in the really heavy stainless steel ball. Okay. So the bigger that mass is in the denominator, the smaller the speed that it would come out, okay? Okay, now, obviously we didn't know anything about springs or energy back in the early part of the semester when we did the projectile lab, but if you wanted to calculate the spring constant for that launcher, okay, this is what we just did, right? Initial energy was potential in the spring, final energy when it exits is kinetic, okay? We just had this, initial potential equals kinetic, okay? But now I want to calculate the spring constant. Okay, halves go away. All right. So I took the mass of the yellow plastic ball. Okay, I put that on the scale. Okay, in terms of x, we use the medium setting, so I had to measure with a ruler how far back that was compressed. That was about 5.5 centimeters. Okay, and from students' lab at that time, okay, a lot of people got the launch speed, okay, when it was on the side of the table and they launched it, made a bunch of dots, and they found that launch speed. That launch speed was about 450 for a lot of people, centimeters per second. Okay, that's about 4.5 meters per second, right? That's about 9 miles an hour or 10 miles an hour or so. Okay, so I put in the mass of the yellow ball, I put in the kind of average speed that people got during that lab, and I measured how far the spring is compressed, and that gives you the spring constant for that spring. So yeah, the manufacturer could have printed the spring constant on the side of the launcher.